Thank you, Chairman, for introducing me. My topic is electrochemically active biofilm-mediated green synthesis of silver nanoparticles in water. So, actually, until 1999, it was believed that biofilm, most of the biofilms are harmful to human beings and industrial products until 1999. So, some recent research suggests that some electrochemically active biofilm can be utilized for many types of application, especially microbial fuel cell and some types of bio-inspired materials like nanowires, some pyrazine. Pyrazine is a corresponding biomolecules, and there are many C3, C4 chemicals. That means using electrochemically active biofilm, we can produce numerous number of chemicals. And especially microbial fuel cell is one of the attractive application of electrochemically active biofilm. So very recently, we found that this electrochemically active biofilm can be utilized for the synthesis of nanoparticles. So it was very recent finding in using electrochemically active biofilm. So there are numerous reports to make nanoparticles using biological entity like bacteria, and it was the first ever report using a bacteria synthesizing silver nanoparticle. You can see this pseudomonas cell, and the nanoparticle is produced on the cell wall. So normally this type of biological process will give nanoparticle inside the biomatrix, and you can see the nanoparticle size is very high, and also it produced on the cell. So this is another report using lactobacillus strain. Here also you can see nanoparticles are bigger in size and also produced most of in the cell wall. So it is very difficult to separate from this type of biological method. And we can use the fungus also to produce nanoparticle. Here a verticillium. So here also nanoparticles produced on the cell surface. So normally, and also it is taking a long time to produce nanoparticles. So we want to overcome this type of difficulties in order to get a good feasibility. So we produced silver nanoparticles using electrochemically active biofilm. You can see a graphics. We just used a carbon paper. And carbon paper is just a support for biofilm. You can see the carbon paper and electrochemically active biofilm sticked on the carbon paper, and we used the sodium acetate as an electron donor. So this here we oxidize sodium acetate to electrons. So normally these electrons are highly in reducing power. So this electron will rapidly reduce the silver ions in the solution, giving nano size. So this new mechanism for synthesizing nanoparticle using electrochemically active biofilm. So then how we made this electrochemically active biofilm? It is very simple, because we used this anaerobic sludge. You know, anaerobic sludge contains thousands of bacteria. So we used this anaerobic sludge as our electrochemically active source, and we used the carbon paper as a support for the electrochemically active biofilm. So what we did, we used a 250 ml bottle, and we filled. We used the distilled water as our solvent. That means we didn't use any type of organic solvent, just distilled water, and we dipped the carbon paper in the distilled water. So and added this 10 ml of anaerobic sludge into the solution, containing silver nitrate, our precursor, and sodium acetate, our carbon source or electron donor. And obviously we want to maintain the anaerobic condition, so we passed the nitrogen gas for a short time, around 10 minutes, to make the anaerobic condition. So just dipping our carbon paper into a solution containing anaerobic sludge and sodium acetate and electron donor. After 2 days, we removed this anaerobic sludge and we used only the media. That means the second step, we didn't use the anaerobic sludge, just used the carbon paper and our media. Then we kept around 1 week, and made our electrochemically active biofilm. Normally, these electrochemically active biofilms are living in nature, so we can utilize many times this electrochemically active biofilm. So we challenged this electrochemically active biofilm to a silver nitrate precursor and sodium acetate as electron donor. So this is our analysis step. We did TM to know the morphology and size of the nanoparticle, and SAD we know to see the crystalline planes, and EDS to see the elemental composition, X-ray diffractometry to see the crystallinity, UV analysis, it is very famous in the nano to see the SPR band, and paper disk diffusion method to understand the antibacterial property of the nanoparticle, FTIR, to see the functional moieties. So this is our term image. You can see the term image, the nanoparticles are extremely small. Normally using biological method, it is very, very difficult to get this type of nanoparticle size. So it is more or less monodispersed, and size is very small, and from the histogram you can see the nanoparticle is mainly folding 1 to 5 nanometer scale and with an average size of 3.6 nanometer. It is never reported using a biological method to this type of extreme small size, and you can see there is no remarkable aggregation. So we can see highly monodispersed nanoparticles. So this is SAD pattern. You can see several crystalline planes showing the polycrystalline nature of the nanoparticle, and this is high resolution TEM. You can see there are some fringes and very crystalline domains showing that nanoparticles are polycrystalline in nature, and the size is around 4 nanometer scale. So this XRD pattern is very typical for silver nanoparticle to getting some different planes. And if you look at this, there is no other peaks other than silver peaks, which is showing the high purity of the nanoparticle. Something is happening in the nanoparticle, like silver oxide is forming. Correspondingly, there will be some peak here. But there is no peak, other peaks, only the silver peaks showing the high purity of the synthesized nanoparticle. So we know normally nanoparticle giving some SPR band. So we are using UV spectroscopy. Normally silver nanoparticle giving the SPR band from 380 to 450 range, depending upon the size of the nanoparticle. So we got our SPR band around 380 nanometers, showing the SPR band of SPR property of the nanoparticle. So this is our EDX spectra of silver nanoparticles to show the elemental composition. You can see very intense peak of silver, and this carbon peak is coming from the carbon coated copper grid, because we are using TEM machine to see the EDX spectra. So normally we will get some carbon peak, some silicon peak, and sometimes oxygen peak, because sometimes this copper grid will oxidize. So it will give a more oxygen peak, and carbon peak is coming from the TEM grid. So then the second stage, we just want to know the effect of cysteine on the nanoparticle synthesis. So during the synthesis process, we add cysteine to understand what is cysteine is acting on the synthesis process. So when we add cysteine, the reaction rate dramatically reduced. That means it took 24 hours to complete the reaction. Meanwhile, without cysteine, it took only 2 hours. So we can see the nanoparticles are assembled. We can say a programmed assembly, because on the surface of the nanoparticle, the cysteine is capped. So there will be a high tendency of the hydrogen bonding between the nanoparticle and giving some programmed assembly. So we want to know this is our nanoparticle silver, and this cysteine containing a thiode group and one COH moiety and another amine group. And it is well known that this SH thiode group is high affinity towards the nanoparticle. So we did FTIR, and these two peaks are corresponding to carboxylic group of the cysteine, and these two are the corresponding to, this is corresponding to amine group, and these two are corresponding to carboxylic group, and this is corresponding to carbon CH bond. So normally if you want to get some peak here for thyroid group, around 2500 region, but it disappeared. That means there is a possibility of this SH group may bind with the nanoparticle. So if it disappeared means the SH group bind with the nanoparticle. So we just conducted a preliminary antibacterial test on E. coli and Pseudomonas. You can see this silver. We used a control as the distilled water and the canomycin as a positive control. You can see almost the silver is competing with the canomycin. Canomycin is a very well-known antibiotic. So our silver nanoparticle is also giving a high antibacterial properties. You can see that here the paper is almost inhibition zone we can see like the canomycin. So it was just our preliminary result on the antibacterial properties. So then normally there will be question what is the advantages of our method. There are many advantages because I already said when we are visiting biological entities like fungus or bacteria, normally it will take long time, normally 24 to 96 hours. But in our case, it took only 2 hours. That is, the reaction is rapid. And nanoparticle is very important because nanoparticles is around 3.6 nanometers. But in the case of other methods, microbial synthesis, it will be range to 10 to 15 nanometers, sometimes 100. So it will vary with another microbial synthesis method. And this is very important. Nanoparticles produce extracellularly. Meanwhile, most of the microbial synthesis produce nanoparticle intracellular. So it's very, very difficult to separate from the biometrics. So here we can just separate. So separation is very easy and because of the extracellular production. Then monodisperse. Because normally the biological method will give highly polydispersed nanoparticle, but in our case we get a more or less monodisperse, which is very important for practical application. If you want to apply for some electronic device or something, we want to get a monodispersed nanoparticle instead of polydispersed. So totally the proposed method giving a high advantage over the previous report. So now we produce only silver nanoparticle, and recently we produced gold and platinum, and maybe we will conduct more research on this. So thank you for your attention.